Any object that has a type of motion where it keeps following the exact same path and every cycle takes the same amount of time as the previous cycle, we refer to that as periodic motion. So swimming laps in a pool is not periodic motion. You keep following the same path repeatedly. However, there's no guarantee that each lap takes the same time as any other. But there are a lot of systems where the time it takes for one full cycle is always the same. In fact, the orbit of a satellite is a form of periodic motion. Well, the behavior of a mass that vibrates back and forth on a spring is also periodic. So is the motion of a pendulum. In fact, those examples aren't just general periodic motion, they're a subset of that known as SHM, which stands for simple harmonic motion. So I want you to imagine what would happen if you took a mass attached to a spring like this, and then you pull it back from its what we call equilibrium position, which is just the point along this x-axis, and we're assuming the ground is frictionless. The equilibrium position is the point on the x-axis where the spring is neither stretched nor compressed, but at its relaxed length. So now we take the object, we grab hold of it, and we pull it back so that it's sitting at some position that's positive on the x-axis. I use the symbol A for that initial position, where A represents something known as the amplitude. Just based on the law of conservation of energy, if you release it, there's no way it's going to compress when it goes to the other side and then come back and stretch even farther than the point you released it from. So whatever point you release it from to set it in motion represents the maximum displacement it's ever going to have. And so the language we use is we say that represents the amplitude of the motion. So indeed, the object is going to move to the other side after a quarter cycle. When you let it go from rest, V naught equals 0, it moves toward the equilibrium position, has velocity at that point, so its inertia carries it past the equilibrium position. The coils of the spring get compressed. Now we've reached half a cycle, and then it moves back toward equilibrium 3/4 of a cycle, and then returns to the point you released it from in one full cycle, or one full vibration, or one full oscillation. So we want to see if we can derive an expression that gives us the period of that motion. How much time should it take for a mass attached to a spring to complete one full vibration? So here we see the overall motion. The position starts out at positive A. When it's fully compressed, we say the position is negative amplitude, and of course you understand the idea of the equilibrium position. So A is a fixed value, or a constant if you will. However, x is a variable, and it's a variable that's bound by these upper and lower limits. The greatest value x will ever have is positive A, and the smallest value is negative A. And so the position varies in time. We might imagine what's the position after 2.5 seconds, or we could say this: how much time will it take for the object to reach this position right here? So the object is going to be located anywhere within these bounds as time passes by, and exactly where it's located should be described as some mathematical function. So position is a function of time. X equals f of t. Now we can set our origin and time anywhere we want. We could grab a stopwatch, pull the block back to the release point, and at the moment we let it go from rest, hit the start button on our stopwatch, and so time t equals 0 when x equals positive A. Although I think we'd be allowed to pull it back, release it from rest, and don't hit the start button yet. Wait until the object reaches this position before you hit start and move your origin and time to an initial position here. Either way, the object is going to vibrate, and so its motion when graphed looks sinusoidal, meaning let's just plot out what we know. Let's go with the first case. Let's say we begin timing the motion at the moment we release it at point x equals positive a. Then right at the moment it's released, the initial position is positive a, and after a quarter cycle, it makes its way to the equilibrium position. After half a cycle, the spring is compressed and x equals negative a. After 3/4 of a cycle, it's back to the equilibrium position, and after one full cycle, it's back to the place you released it from. So that's t equals capital T. When the time is one full period of motion, then you've completed one full cycle of oscillation. And from there on, it'll just keep doing the same thing. So you can see this looks like a graph of cosine. Now, what if we took the alternative approach and began timing it once it first reaches the equilibrium point? Then at time t equals 0, the initial position would be 0, and after a quarter cycle, it would travel to this position where x equals negative a, and then, and after half of a cycle, it would be back to the equilibrium position, but moving in the opposite direction. After 3/4 of a cycle, it'll be an extended spring, and after one full cycle, back to where we started timing it at the equilibrium point. And so you notice either way, we're looking at one full period of motion and one cycle. It's just in this case, the graph looks like a graph of negative sine. So we have a few possible guesses that we're going to use at what's the best way to write position as a function of time. Let's let Newton's laws guide our thinking. There's the object at the equilibrium position, and there's our relaxed spring, and maybe we've pulled it back this far to set it in motion. I'm interested in the forces that are acting when it gets here. Now, that's not x equals 0. That's not x equals a. This is just x equals x. Okay, so this is just one of these random positions that's bound, and something less than positive a and something greater than negative a. Okay, right here. So make a free body diagram. I think the ground pushes up. Now we suggested this is on a frictionless surface. So anyway, the ground pushes up with normal force. Gravity's pulling down with a force mg, but those are just going to cancel each other out, and you're just left with one more force. There's no friction, but the spring is pulling on it, and the spring's pulling back toward the equilibrium position. They often refer to the force exerted by a spring as a restoring force. And restoring forces are the type of forces responsible for all forms of simple harmonic motion. When a pendulum swings, it's the same sort of thing. It wants to return back to the equilibrium position when the string goes vertical. And, well, gravity itself points straight down, but if we break gravity into components, there's a component of gravity that pulls back towards the center, and so a component of gravity is the restoring force on a pendulum. So we'll hear about restoring force a lot in this unit of study. In this case, the restoring force is governed by Hooke's law. We say F equals, I'm tempted to say kx, but I suppose I have to put a negative sign. The reason for the negative sign, you can see in our choice, we're imagining the object to the right of the equilibrium position. So x is positive, but the force, the spring, is pulling on it to the left. So the force is negative. And these two are always going to be out of cycle with each other. Whenever the position is positive, the force is negative, and whenever the force is positive, the position is negative. So F equals negative kx is the correct expression. Because gravity and normal force have canceled one another out, then the net force acting on the object is this restoring force of negative kx. Let's go through a derivation here. By Newton's second law, net force can be replaced with ma, but acceleration can be thought of as the second derivative of position with respect to time. If I divide both sides of the equation by m, then I have an expression that says the second derivative of position with respect to time is equal to negative k over m times x. Now keep in mind, x represents some sort of function of time. So are there any mathematical functions for which you can take the second derivative, and in doing so, the second derivative of that function is just equal to a negative constant multiplied by the original function? Well, we went through this exercise in our previous example for the object that falls through the center of the earth. If you drop an object, then there's a restoring force provided by gravity that wants to pull the object to the center of the earth. Its inertia makes it overshoot. It's gone through half a cycle by the time it reaches the other side. 3/4 of a cycle, it's back to the center of the earth, and in one full cycle, it returns to the point you dropped it. And we found that if we made a guess that position is equal to the radius of the earth times cosine omega t, then by taking the second derivative of this function, we were able to show that the second derivative was equal to some negative constant multiplied by this very function itself. So we're going to take the same approach here. Let's make our guess. Well, we have a really good educated guess this time. We should either guess a function that describes the shape of this graph, or we should guess a function that describes the shape of this graph. Let's go with option number 1. Let's just guess that the position of the vibrating mass on a spring is equal to some maximum value of x times cosine of omega t. Then our first derivative, which would give us an expression for velocity, would be equal to negative omega x maximum sine omega t, and acceleration, the second derivative, would be equal to negative omega squared x maximum cosine omega t. However, what is this? X maximum cosine omega t is just x itself, so we've done it. The second derivative with respect to time is equal to a negative constant times x itself. So can we correlate this result we know must be true based on Newton's second law along with our guess, which gives us this expression? In other words, make the comparison, and what do you see? The only way these two can compare favorably is if omega squared is the same thing as k, or negative omega squared is the same thing as negative k over m. Negative omega squared must be negative k over m. And if so, our guess gives us a result that matches the result we know should follow from Newton's second law. We can cancel out the negative signs, and this just means omega is the square root of k over m. Now, period, frequency, and omega are all related to one another, and they're all helpful in helping us determine how quickly the object oscillates. When the frequency is high, the period is small, and vice versa. Well, standard frequency is just angular frequency divided by 2 pi. So if omega is the square root of k over m, that'll give us some value in radians per second, meaning just divide the stiffness of the spring by the mass of the object attached to the spring, and you have idea how many radians per second describe its motion. If you want to know how many cycles per second, then we have to divide by 2 pi. So the frequency would be 1 over 2 pi times the square root of k over m. Now, if you want to know just how many seconds does it take to complete one vibration, now you're talking about the period, but period is the strict inverse of frequency, so the period would be 2 pi times the square root of m over k. That's the holy grail here. That's what we're after. We want to know how much time should it take. That was the question at the outset. How much time would it take a mass to vibrate if you pull it back on a spring and let it go across a frictionless surface? And there you have it. The period depends, not surprisingly, on the amount of mass and how stiff the spring is. And this makes sense. If the spring is really stiff, this expression is telling us as k goes up, a stiff spring that can apply a lot of force should make it move faster and therefore take less time to vibrate. And by the way, as the mass goes up, it becomes a lot more sluggish, has a lot more inertia. And so with greater mass, you should get greater period. And our result agrees with those predictions. Mass is in the numerator, spring stiffness is in the denominator. What might surprise you is that amplitude is nowhere in the result. The period is independent of A, the amplitude. And that surprises a lot of people. Some people would assume if we compare side by side, what if I had a mass attached to a spring and I only pull it back a tiny little bit, so it doesn't have too far to travel in one full cycle. And then I try again. I take the exact same mass, the exact same spring, but in my second attempt, I pull it back this far from equilibrium and let it go. Well, now it has farther to travel in one full cycle. Why doesn't the period change? Yeah, it has farther to travel, but it also has a more forceful spring engaged on it. Hooke's law says the farther you stretch the spring, the greater the amount of force. And so the two have a canceling effect. The greater distance is negated by the greater speed, and therefore the period ends up being independent of the amplitude. So that's a key feature of SHM, simple harmonic motion. For anything that vibrates with simple harmonic motion, period does not depend on amplitude, but it does depend on other key factors such as mass and spring stiffness. So there's an introduction to the behavior of a mass on a spring. Oh, no, we've got one last thing to correct here. Now we know what we can substitute for omega. Omega in our guessed expression can be substituted with the square root of k over m. What do we substitute for x max? Well, actually that's pretty obvious. The maximum position is nothing more than the distance you pulled it back when you released it from rest. So let's fix our guess just a little bit here. We'll rewrite it. We found a result that the period is 2 pi times the square root of m over k based on a guess that x equals x max cosine omega t. But we can replace that with x equals a amplitude times cosine of the square root of k over m times t. Two important equations that describe the motion of a mass vibrating on a spring, which is one of our prime examples of simple harmonic motion.